Version of the inverse problem seminar. So very happy to have Yang from UC Santa Barbara, which has done a lot of interesting work in high frequency waves, semi-classical approximations, and so forth. And we're happy that he will talk about frozen Gaussian approximation for the fractional Schrödinger equation today. So thank you so much for joining.
Thank you for the invitation. Thanks, Knut and Katja, for the nice invitation. I'm really happy to speak in this seminar, although I'm not talking about inverse problem, but this is something related to fractional Schrödinger equation. And also I'm very happy to see Jim Lawson in the audience. When I was a student, I attended a workshop in UT Austin. I learned not frozen Gaussian approximation, but the Gaussian beam a lot from Jim Lawson. He's really he really taught me a lot. Okay, so this is some work I did actually a couple years ago. So I will, if I miss some details, just stop me and ask. So right. All right. So the topic I want to speak is about frozen Gaussian approximation for the fractional Schrödinger equation. Okay, this is in collaboration with one of my longtime collaborators, Li Hui. He was a postdoc at UC Santa Barbara before, and now he joined Zhongshan University and is an associate professor there now. And Heng Jun is his student, now is studying at Fudan University. Basic introduction for fractional Schrödinger equation. The fractional Schrödinger equation, different from the standard Schrödinger equation, is basically on the kinetic term. It's not like a standard half Laplacian. Instead, you have the fractional power on the Laplacian operator. And how do we define them, or how do we understand them? We can understand that in like a Fourier transform way. So basically, if you have something like this, you can take the Fourier transform, and then by the property of the Fourier transform, this operator becomes with polynomial power, and then you take the inverse Fourier transform. So this is like the way that we understand how the fractional operator means acting on some functions. Okay, and of course, we need to give some requirement on the functions, the regularities, etc., so that all those operations can make sense. For example, if you think about the wave functions in Schwarz class, there's no problem about the integration, right? Okay, so just in case you never heard about Gaussian approximation before, this is like a startup like a classic. So we can talk about frozen Gaussian approximation for the classic Schrödinger equation. This is frozen Gaussian approximation. Basically, it's like you approximate the wave function in the so-called semi-classical regime. So this Schrödinger equation is like a rescaled Schrödinger equation in the sense that we non-dimensionalize the standard Schrödinger equation where you have the Planck number, all kinds of stuff in the coefficients. They are very small, but they are small in the standard units. If you think about atomic units, and they are big as well, right? And because the h bar is equal to 1 in atomic units. So it's really hard to say big and small in the physical units. And then mathematicians usually do the non-dimensionalization. And this is the semi-classical Schrödinger equation that we consider. And in the sense of semi-classical, we say the small parameter after non-dimensionalization is very small. And this is usually due to the size of the material. So if you think about the quantum size compared to the size of material you're looking at, the ratio is really usually related to this small parameter. So we are looking at a relatively large scale problem. And then if in 1D we can do a simple a spectral method to like get some intuition on the solution of this standard semi-classical Schrödinger equation. And when the epsilon is small, the solution is very oscillatory. So you have a big wave packet, and then within the wave packet, the solution is very wiggling. So the envelope is smooth, but due to the highly oscillatory phase function, and makes the solution very oscillatory. And then our goal, numerical goal, is to whether we can do some analysis before we do the computation, so that we can save some computational cost by this asymptotic analysis. It's kind of like the multi-scale expansion technique that we learned before. And however, there are many ways we can do the semi-classical approximation. The most straightforward one is like the WKB expansion, right? This is the standard one. So we propose the ansatz like psi is equal to the amplitude times e to the I times the highly oscillatory phase. We plug in and then we collect orders. For the phase function, we have the Econo equation, and then there are a lot of research has been done on the Econo equation, like because this is the Hamilton-Jacobi equation. It develops singularities even though the initial condition is smooth. Because when you take the derivative, when you take the time derivative of the phase function, and that becomes to be the Force-Burgers equation. And for the Force-Burgers equation, it develops shocks. However, because the Schrödinger equation is linear, there is another concept called multi-valued or the multi-phase solution comes in the sense that you want to keep the superposition principle. When you develop shocks from the Econo equation, you want to add all the phase together. Instead, you want to make it to be propagate in the viscosity sense. If you let it propagate in the viscosity sense, then it gives you only the first arrival waves. There are many. There are many literature related to how should we do the semi-classical approximation, and then later on, James Lawson, the Gaussian beam method, which is a way that you fix it by making instead of geometric rays has no volume, you make it to have some volume, and so that the asymptotic expansion can go beyond the caustic, which is also valid. And the idea behind that is when we do geometric optics, which is a WKB expansion, we treat everything as particles. And then particle does not have volume, so that there could be a possibility when the caustic develops or when the shocks has a formation, and then all the particles come together so that amplitude blows up. And the Gaussian beam method, because we are considering the Gaussian function, Gaussian has a finite volume, so that you completely avoid many Gaussians can come together to one point, so that amplitude blows up and makes this still a valid approximation beyond the caustics. But today, my topic is not about this literature. My topic is about how do we do frozen Gaussian approximation. The frozen Gaussian approximation is also based on asymptotic analysis or the multi-scale expansion, but I will explain the difference between the frozen Gaussian approximation from the other asymptotic expansions like WKB, which is geometric optics or Gaussian beam method. But the idea is actually very similar to the Gaussian beam method, but it's just the way we derive the asymptotic equations are a bit different. It derived the asymptotic expansion is not in the strong form, it's actually in the weak form. It's not like we plug in, we collect orders and we match it. Okay, so the idea is like we approximate our wave function by a linear combination of Gaussian wave packets. So what is the Gaussian wave packet? The Gaussian wave packet is in this form. So it has a Gaussian, if you ignore the phase, so this part in the expansion. Sorry, I don't know why I cannot click it. So this part, the first part in my phase in the expansion is phase, especially when epsilon is small. This is a highly oscillatory phase because think about the sine 100x. So this function is very oscillatory, right? So we apply Euler's formula. So e to the I s will be cosine s plus I sine s, right? And this s is like a p times x or epsilon. When epsilon is small, this is like 100 px or 10,000 px, depending on how small the epsilon is. And the second part is regarding the amplitude. It gives you the decay. So this is the wave package centered in the phase plane. So it's centered in the x equal to q, and with the decay rate, if you think about the standard variance, it's the square root of epsilon in the scale of the square root of epsilon. So it decays very fast. I mean, uh, when I say decays very fast, it's not, it's decays expansionally, kind of like a compact support. It does not have a compact support because expansion only goes to zero as x goes to infinity, but it decays very close to epsilon. Sorry, decays very close to zero after 3 times square root of epsilon, and also has this complex phase. So this is very similar to the Gaussian beam setup. However, the Gaussian beam setup, although there's a phase version, but in the Gaussian beam setup, Gaussian beam can allow this decay rate change over time. And the frozen Gaussian approximation, by the name, is you froze the size of the Gaussian function. So that's the difference in the form of the ansatz of the frozen Gaussian approximation from the Gaussian beam method. Okay, then the last line says, how do we approximate? Because so this wave packet is over determined basis in the L2 space, we are able to approximate an L2 function by a linear superposition of all the Gaussian functions with the proper rates. Initially, how do we get the initial condition for the amplitude or for the wave function? We can do the projection, right? We project this function initially into each of the Gaussian function or the wave packet that we use, and then after we sum them up, because of this overdetermined basis, we are able to recover the initial condition. Okay, and then the trick is we have to let this Gaussian wave packet to have some dynamics in order to capture as a good approximation of the wave function dynamics. And how can we let them to have dynamics? We want the center. So the P is the momentum, is our Gaussian wave packet. Q is the center of our Gaussian wave packet. We let this pair to have some dynamics. And the dynamics it has will be the same as the one that we developed or we derived from the geometric optics. So essentially, it's like the trajectory of the Gaussian wave packet follows the geometric optics. However, it also has some distinct different because it has a volume. So it's not like a particle. It's a Gaussian wave packet. Okay. So the classic dynamics for the standard Schrödinger equation is like this Newton's second law, right? So Q is the position, P is the momentum. So the time derivative of the position gives you the momentum, and the time derivative of the momentum is the force. And for standard Schrödinger equation, the force will be given by the negative gradient potential. And this is the dynamics of wave packet for a wave packet initially at the position little q, initially with the momentum little p. Okay, and then the tricky part, which usually involves a lot of detailed calculations, is the derivation of the amplitude. So how do we derive the amplitude equation? Of course, we learned from our class that we plug in the ansatz. We try to group together those terms that are at the same order, and then we try to make some simplifications in order to derive that. And of course, in order to do that, we have to do some Taylor expansion because we want to focus on one wave packet dynamics first. So when you plug in the ansatz to the Schrödinger equation, we're going to expand our potential because our potential is defined for every x. So it's acting on every x. That means, at the same time, this potential will affect many wave packets which will pass through this position x. But this effect can be analyzed by Taylor expansion. This is what we do in the Gaussian beam approximation. When you have a dynamic Gaussian weights, you plug in, you do Taylor expansion, and then you match the orders in epsilon, you match the orders in x minus q, right? So x minus q is a small parameter or a small number in the sense that because if you look at the wave packet, you know this decays very fast. So that means uh, if you treat it as a compact function, then the compact domain is in the scale of the square root of epsilon, which is the scale of the x minus q, right? And then basically we can make x minus q connect to the order of epsilon. And how do we make them connected? Uh, as I explained in the Gaussian wave packet, x minus q is like the order of the square root of epsilon, so that the Gaussian wave packet has some significant values, right? When I say significant values, means it does not, it is not very close to zero. Okay, so this is a very straightforward way, and this is also the Gaussian beam expansion. Although you may not have to convert everything into the epsilon, but you can convert x max q to the order epsilon so that you can collect all the orders together. Okay, and then if you do this for the frozen Gaussian approximation, actually it does not work in the sense that you can have more equations than your variables. This is due to if you if you know something for the Gaussian beam method, it's easier to understand because the reason the Gaussian beam method has a dynamic weight function is because you need a degree of freedom from the dynamics of the weight function, which is that describes the fat of the Gaussian, and make the Gaussian to be sometimes fat, sometimes thin, and this dynamics makes this asymptotic to be a perfect match. So you're gonna have the perfect equation with the perfect unknowns. And this is important. Actually, I like the theorem of the Gaussian beam method from James' previous work, which is it proves the dynamics of the Hessian function for this Gaussian function satisfy the Ricardo equation, and this Ricardo equation do not develop singularities for all the time, as long as initially the setup is proper. Okay, so for frozen Gaussian approximation, unfortunately, we lose this Hessian function, so we lose the dynamics of the Gaussian. And how can we balance the number of variables with the number of equations? And this is the kind of the weak form asymptotic that I talked about at the beginning. So in order to try to reduce the redundancy, try to reduce the overdetermined conditions for the number of the unknowns that we had, we have to do a trick of the integration by parts. So this is the integration by parts trick. So as I said before, x minus q is in the scale of the square root of epsilon. However, if you think about this in this weak sense, which is like you think about you are matching the asymptotics not one by one. We're not deriving one wave packet dynamics, but we are trying to derive the effective dynamics for all of the wave packets in the sense that each wave packet is not a symptotic solution to the Schrödinger equation, but the summation of the wave packet together. So you integrate with Q, integrate with P, will be the symptotic solution to the Schrödinger equation. And then in this sense, because this is you have the integration, so one way you can do is you can do the integral parts, and it's kind of a technique, but technical. But it is true that you can find some cancellations when you do this integration. So when you think about this x minus q term in this integration sense, ideally by the intuition we know this will be epsilon to the power of half because that's the order of x minus q. However, when you do the integral by parts, the first order, the epsilon to the power of half will be cancelled. And instead, you can have this is like an epsilon term. So x minus q in the integration sense will be at the order of the epsilon. And the cancellation only happens for the odd power of x minus q. It's kind of like because of x minus q times this and times the exponential, it's kind of like you have a polynomial multiply on a Gaussian function, and then you integrate it. So think about the integration of y times e to the negative y squared over 2. Because this is an odd function, when you integrate y from minus infinity to infinity, this will be 0. It is only non-zero when this is y to the power of even powers, right? It's like a y squared, y to the power 4. And this is the second line of this lemma. The second line of this lemma is x minus q to the even power. And then you get back to epsilon as well, right? So when you have the odd power, it cancels and then goes to the next even power, which is x minus q squared. When the linear order is even power and then there's no cancellation, you still have the epsilon. So that means, in this sense of the symptotic expansion, we are able, the x minus q term will be treated as the same order as x minus q squared. So that makes the asymptotic expansion very complicated. We have to be very careful in order to do not miss terms, right? Because it's very easy that we match when we do the Taylor expansion. It's a bit weird to think about when you do the Taylor expansion. The first order of your Taylor expansion will be actually the same order as your second order Taylor expansion. That's weird, but this weird thing happened when you think about this integration because of the cancellation term. Okay, so that means the leading order of the x minus q is actually when you do the summation is 0, and only the remainder term is matters. Okay, and then by this lemma we are able to derive the equation for this amplitude, and this amplitude is related to this is so-called the complex valued matrix Z. So it's kind of like a dilation to I won't say it's a dilation of the wave packet because the wave packet has a frozen shape. It's kind of the dilation of the QP distribution of your Gaussian wave packets. So think about, it does not make much sense in the continuous sense. So think about the discrete sense. So initially, we approximate the initial condition by a summation of the finite number, could be many Gaussian wave packets. And then we usually do the uniform grades, right? So we do the uniform grades on Q, uniform grades on P, and we use this uniform distributed wave package as an approximation for our initial condition. And then later on, although initially they are uniformly distributed, but when you let them go according to the dynamics of the Hamiltonian dynamics, which is the geometric rays, then you have some dilations of this distribution, right? And this Z describes dilation of this distribution in the complex sense. So these are partial. So capital Z is the matrix. So the partial little z is kind of like a gradient. So it's a gradient with respect to the initial position. It's a gradient with respect to the initial momentum. And its complex value. And its complex value in the sense that it happens here. So in order to see the cancellation, we have to make up some derivatives on the phase function so that you can appear as the x minus q term. And then you do the integration by parts. That's why you see this partial z acting on this b. So, when we derive this lemma, we're going to represent this x minus q by some partial derivative with respect to little q, linear combined with some partial derivatives with the little p on the phase function. And then, we can integration by parts so that the derivative will be acting on B. And then there will be some matrix C coming out from there. This is a little bit technical, but also, this is the most tedious derivations for the amplitude equation. But usually for my empirical experience, if we do the calculus careful enough, usually we can simplify the amplitude equation in a very simple form. Although the derivation has a lot of details, but in the end, the equations are usually very simple. Okay. So then for the fractional Schrödinger equation, essentially the derivations are very similar. The only difference is first, the Hamiltonian dynamics will be different. So the new Hamiltonian dynamics will be updated as TO, the momentum plus the potential. So TO, the momentum for standard Schrödinger equation will be c squared over 2. That's why when you look at the standard Schrödinger equation, you have the P, right? This is the partial H, partial P. This is the partial A, negative partial H, partial Q. So for fractional Schrödinger equation, this will be the partial T, partial P, and this will be the negative partial gradient, partial Q. So, and then, I mean, essentially the reason I want to mention, I explain the derivation using the standard Schrödinger equation is because the derivation for fractional is essentially the same. And the equations are the same for the amplitude equation. Okay. So now we talk about the accuracy. So the big difference between the fractional Schrödinger equation and the standard Schrödinger equation is in the analysis side. So for the analysis, the Schrödinger equation are very nice. The Hamiltonian is very smooth. And however, for the fractional Schrödinger equation, the Hamiltonian has a singularities at p equals 0. And that makes the analysis different from the standard Schrödinger equation. But let me also, start with the standard Schrödinger equation first. So when we do the standard Schrödinger equation, how do we analyze the accuracy of frozen Gaussian approximation? And this is the standard way that we do, right? So usually, in order to analyze the accuracy of the asymptotic expansion, we keep more asymptotic terms in the expansion, and those are considered the remainder, right? And when we rigorously bound the accuracy, we actually looking for the rigorous bound for the remainder term. So, of course we have to make some assumptions. Usually the assumptions we make for the Schrödinger equation is the initial conditions are in the Schwarz class. So it decays fast so that we can have an efficient approximation of the initial condition using the linear summation of the Gaussian wave packet. And then we compute the remainder terms. The remainder terms means what? Means, we are not only using so the remainder terms basically means when we approximate the wave function like this, this is the asymptotic part. We are going to consider A plus epsilon A1 in here plus epsilon squared A2 plus dot dot dot, and then we plug in. Then all the terms related to A1, A2, etc. will be considered the remainder. And we will be also contribute to the error of the approximation. So then we keep the A0 plus epsilon A1 plus epsilon squared A2. We plug in, and then we consider those terms related to A1, A2 as the remainder terms. And then we need the energy estimate to bound them. And once we found the uniform bounds on the amplitude and the Jacobi matrix, when we say the Jacobi matrix evolution, I mean the evolution of the Z. So those terms we need to show the uniform bound on Z inverse. Essentially, that means we have to prove a lemma to show that Z will be always invertible for all time. If Z is not invertible for some time, then we know the amplitude will blow up and there will be some unbounded term in the remainder, right? Because the remainder will not be only A1, A2. There will be some crossing terms of A1, A0. Okay, so right. And the approximation is measured in L2. And so this is a more detailed description on what I just described. So we plug in the ansatz into the Schrödinger equation. We only keep the term, so we treat the A1, A2 term as R. I mean, it's very messy so that I don't put the detailed format in here. I just use in R. And no matter what messy it is, we under the assumption of the solution is in the Schwarz class, we can show that, right? So one can show that this R will be bounded, and then the remainder will be in this term, right? And then we apply the energy estimate. This energy estimate, I have to say, the one I described here is not very sharp. We can do a sharp estimate like the Hagedorn dynamics. So Hagedorn has some more careful dynamics and estimate so that um, we can estimate so that it's kind of like the Hagedorn dynamics can generalize the estimate to not finite time t, but for the Ehrenfest time. This estimate can be valid for log epsilon. T can be a log epsilon in the log epsilon scale. And then so we did some detailed work to bound this remainder, and then once R is bounded, we know this L2 accuracy will be the big O epsilon. So this is the first order FGA approximation. And of course, this order is not like a one-time thing. We can systematically improve the accuracy by adding more corrections, right? Adding more corrections on the on the amplitude, right? We can derive an equation for the corrections on A0, right? So we can derive another amplitude equation for A1, and then if you use A0 plus A1 as the asymptotic expansion, then you can improve the accuracy to be the big O epsilon squared. And this is not optimal. So this is, the results I list here is not optimal. If you do the Hagedorn dynamics, this does not have to be a finite time. It can be the Ehrenfest time. Okay, so this comment is actually for the first order Gaussian beam method, the accuracy will be epsilon to the power half. The reason for that is because for Gaussian beam method, each Gaussian wave dynamics, it is a asymptotic solution to the Schrödinger equation. And because it used the dynamic Gaussian weight and the Hessian function. And in that sense, when you make the Gaussian wave packet do not have the same weights, then it's not always you have cancellation effect. Although sometimes the theoretical results can be epsilon to the power half for Gaussian beam method. In reality, sometimes you may see higher order in numerical, higher order convergence for Gaussian beam method because of the cancellation. But since the wave dynamics is dynamic, the cancellation may not always happen. Okay, so now compared to the standard estimate for the Schrödinger equation, the fractional Schrödinger equation is formally is in the same way. So we can still, it's just the equations are different. The ansatz is the same, and you plug in, of course, the remainders will be the same. But the strategy is like we try to bound, right? We still try to find a bound on the remainder term, and then we still do the energy estimate on this error equation. And then once we have that both sides done, we can conclude as we did for the standard Schrödinger equation that the accuracy of this fractional Schrödinger equation. However, the problem, the reason we have to do some more work is we'll take the higher order derivatives with this fractional Laplacian operator. It has a singularity at p equals 0. For standard one, you have this is p, right? When you take the gradient, that is p. But for the fractional one, you have the singularities, it's not p. So how should we, how can we estimate for the fractional Schrödinger equation? First, we have to regularize this, and we hope there's a uniform bound when you take the small parameter to be to go to 0. So this is the first thing we have to do. We have to regularize so that it does not have the singularity at p equals 0. And we have to apply some cutoff in the phase space to exclude points near p equals 0. So that is, when we do the dynamics, right? So when the dynamics, although so when we regularize our fractional Laplacian operator, our Hamiltonian has no problem. So that means there's no problem about our dynamics. So our dynamics will be, always well defined. However, when you let the wave packet go according to the Hamiltonian flow, there's still a possibility that these flows are getting to the forbidden region. Getting to the forbidden region, which is p equal to 0. And then when your dynamics getting near to there, although the chance to get there is very low, but once they get there, there's still some problem. So that means we have uh, to do some cutoff in the phase space so that when it gets there, we're gonna ignore it, and we cannot really ignore it. We have to estimate how much Gaussian wave packet can go there. So if it's only very little Gaussian wave packets can go to the uh, can get into p equals 0 region, then we are still able to develop the 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 accuracy estimate. So basically, this is what we have done. So the delta is the parameter for the smoothing the Hamiltonian. The omega is the cutoff for the dynamics, which is we only we can only do the standard Schrödinger analysis on those Gaussian wave packet, which is having the dynamics under the smooth Hamiltonian and excluded from the p equal to 0 region. And then, this is not all, right? So we have to say, there will be a uniform estimate on our smoothing. There will be an estimate on those Gaussian wave packet who can get into the p equal to 0 region. And this is the cutoff. So this, this is what I explained. So we are doing estimate on this filtered amplitude. And then that changed the results. So we are not able to have the first order accuracy for our Gaussian wave packet as we did for the standard Schrödinger equation. The estimate for this actually depends on the dimensionality. So for lower dimensionality, this is the results that we get, and this is for higher dimensionality. And why this depends on dimensionality, as you may already notice, is because of the singularity that we had. The singularity is when you take the high order derivatives on the potential, sorry, not on the potential, on the Hamiltonian, which is the operator T. On different dimensionalities, the singularities will be different. And so in higher dimensions, we can control this in the singular term, right? So P is 0, it's like the trouble region, right? And for the higher dimensionality, we are able to bound those terms easier. And then for lower dimensionalities, those terms are less integrable. And that's why we are able, we cannot have a uniform bound for the same, in terms of dimensionality. Okay, so then so basically this is the analysis part that we did, and also we did some numerical testing. My empirical experience for symptotic expansion is like usually when you do numerical, you kind of have a little bit better results than analysis, in the sense that it's not always to have some example that exactly happens in the worst scenario of the analysis. If we just do like, so if you look at the symptotic analysis paper, geometric analysis for high frequency wave, people usually do is the initial WKB type initial condition. And this type of initial condition is kind of very nice. When you do the numerical, you just follow the symptotic equations you derive, and the results is usually better than you think, than the theoretical predictions. So we did this the standard setup. So we consider the fractional Schrödinger equation in both one-dimensional and two-dimensional case. We consider this WKB type initial wave packet. And apparently, it's not easy to find some analytical solution for this fractional Schrödinger equation as a reference solution. But if we consider decay, a highly decay initial condition like a wave packet, we are able to think this is a periodic boundary condition as long as the dynamics does not touch the boundary. So that we can use the spectral method, which is highly accurate, to compute that as a reference solution. This is the setup that we had for numerical. So spectral method as a reference and WKB initial condition. So this is the wave packet going to the right, right? The reason I know going to right is because the phase function, the velocity gives you the 1 to the right. And the potential is the cosine potential, and this is the short time dynamics. Because the reason we did short time dynamics is because for spectral method, we have to make sure the wave packet, I mean, the wave function does not touch our boundary. And if it touches the boundary, then the spectral method the periodic boundary condition that we had will not be like the Cauchy problem, right? Because some waves coming back. So we did the short time dynamics to avoid this initial condition touch our boundary, so that our reference solution provided by the spectral method is still a good reference. And also, I want to mention that in order to have a good accuracy, we have to take the mesh grade and time step to be very small in the spectral method, because the solution, the wave function is very oscillatory, and we have to resolve the oscillations by using small mesh. And this is the results that we had for 1D case. So so this is so the two figures are plotted under different regularization. The left one is regularized in the sense of epsilon. The delta, I mean the delta. If you forgot, the delta is how we regularize the Hamiltonian. And for different regularization, we have different convergence rate. And it's not surprised that if you regularize smaller, you may have a better convergence. If you regularize more, apparently it will be more away from the true solution. And this is the 2D setup. So it's also a Gaussian packet, and Gaussian packet. It's a Gaussian shape initial condition in the WKB form. And the velocity is 1, propagating in the x2 direction. And this the reference this. Right. Yeah, so essentially this is I think this is essentially the same setup of the 1D. Just we put it in the 2D direction, two-dimensional directions. And this is the same thing that we did for the one. I mean, essentially the 1D, 2D, it's just a difference of the numerical implementation, and we use different initial conditions. 1D is just a one Gaussian function in one-dimensional. 2D is like a Gaussian function in two-dimensional. And actually, it's one-way propagation in a 2D case. It's not like propagating to a different, I mean, it's like this initial condition propagating initially velocity is in the x2 direction. And we have consistent numerical results for 2D. So when you regularize more, you're going to have a slower convergence. Okay, so basically, as a summary, what we did is we analyze, we derive and analyze a frozen Gaussian approximation for fractional Schrödinger equation, and the derivation is essentially the same as one did for the standard Schrödinger equation. However, the main contribution part is on the analysis. In order to get analysis on the accuracy of the frozen Gaussian approximation for fractional Schrödinger equation, we have to do two things. We need to regularize the Hamiltonian, and also we need to make a cutoff, which means we have to analyze the filtered amplitude equation. And then we did a numerical testing on the 1D, 2D case of the frozen Gaussian approximation. And this is the paper that we post on the archive. Okay, so that's all I want to say. Thank you so much.
Great. Thanks so much for very nice talk. So it's interesting techniques, interesting problems. So now the floor is open for questions. So if you have questions, please unmute yourself and ask questions. So
I couldn't hear clearly, sorry.
Yes.
Your superposition has the factor phi equals P2, and the phi is e to the pi little phi over epsilon. Now, in the standard Gaussian approximation, the tension of the little phi satisfies the Riccati equation. But you don't seem to use that.
I only heard the Riccati equation, the Hessian function, and sorry, I don't get. Sorry, I don't know. Maybe my connection was not so good. And sorry, what's the question again? I only heard Hessian function, Riccati equation. I think this is the.
Might be the simplest form of that question. Because you seem to say that the phase in the Gaussian is independent of where you are on the trajectory. That's not what you mean here. Oh dear, it's very hard to. There could be something wrong at this end or something wrong at your end, so we can't hear each other. But that's okay. I don't want to take up too much time here.
So very long trajectory and.
There are, of course, the trajectory. And you have, because of the Gaussian method, you have different equations for the amplitude. Take advantage of cancellation because you have a superposition. I was wondering what happens to the other half. I mean, the Eisenhower equation for the Hessian for the phase. I'm sorry, here. I could talk louder.
Yeah, I try to hear. So basically, I think you are. I think I heard there will be cancellations. Do we have? I mean, Gaussian beam, frozen Gaussian, they will have different amplitude equations, right? And for frozen Gaussian, we have cancellations. And you also mentioned the Econo equation, and you are wondering. maybe different trajectories or something? I didn't get it. Sorry.
Go back. Go back to some of the very first slides here.
This one? Even back
Pretty good.
here?
Good here.
Uh-huh.
Under the integral, we have phi, d of t, d of t, and x inside the integral. That's the Gaussian part, which you're taking a superposition of here.
Right.
Now, that part looks like a Gaussian. But what determines the evolution? That has e to the epsilon little phi of dx. And how does that work? I mean, I can't quite understand. What is phi sub phi of t dx of x? What is it?
So you mean phi is real, or phi should be complex, right? I mean,
You say it's a Gaussian wave packet centered at q of t, p of t. But the Gaussian wave packet in standard Gaussian b has a variance that's changing to t. But that here.
so if I understand correctly, I think I mean the difference is for Gaussian beam. If you think about Gaussian beam solution, it is a symptotic solution, right? No matter you do the linear superposition or not, right? But for this type of the Gaussian-based, Gaussian wave packet dynamics, if you do not do the linear superposition with all Gaussians, it should not be a solution. Should not be a symptotic solution.
Yeah.
Right. Right. Yeah. Yeah. Right.
Okay. Thank you very much.
All right. Thank you. Thank you. Thank you, Jim. Knut, you mute yourself.
Some technical challenges here. So I was just wondering, when you do the analysis and you have these regularization parameters, delta and omega,
Yeah.
do you sort of do a joint limits, choosing this depending on epsilon, or a sort of a sequential limit?
Numerically, we did choose to relate it to epsilon, but for
Yeah.
I mean, so I mean, sorry, I just try to understand. Are you asking about principle of choosing delta, or I mean, just any?
Yeah. So for the principles, say symbol, how do you choose delta depending on epsilon, or?
Yeah, we choose delta depending on epsilon, but numerically you can choose basically by empirical experience.
Yeah. But there is a sort of an optimal way of doing it, or
Oh, that's a good question. That's a good question. We haven't thought about that, whether there's an
yeah.
optimal, but we did some numerical tests, and the seems, you know, we hope delta can go to zero
Mm,
faster.
yeah.
Faster the better, and but sometimes, if it stop working, then you empirically have to go back a little bit slower.
Right, yeah.
It's a good question. We should think about that, whether there should be a way that we can optimize truth data in the sense of epsilon.
Mm,
Yeah, thanks.
sure. Is there any other questions for you?
Hi,
Yeah.
just a quick question. So when you do this numerically, do you you write this in this main convergence result? You've written like this psi epsilon delta FGA omega. So here you are imposing numerically the regularization in delta as well as omega. Is that right?
Yeah, that's right.
And if you were to numerically just go ahead and try to solve or do the expansion with the FGA without doing the regularizations, do you see the convergence or do you see some kind of a blow up here?
Oh, that's a good question. So basically, if you do not do the regularization and you do not do the cutoff, if you, you see blow up. That's really depends on the detailed numerical simulation that we are looking at. If, we were unlucky and some of the Gaussian wave packet gets close to the forbidden zone, then you see the blow up in your amplitude.
Okay, because I think sometimes in these kind of numerical settings, you somehow implicitly end up imposing the regularizations, even if you don't do
Right.
the method itself will somehow impose these
Yeah,
regularizations.
for example, if you use RK4 as the ODE solver for those
Mhm.
solving the ODE equations, then you have the numerical dissipation that introduced there, and you may save you out of the blow up, but sometimes, that's kind of the linear stability issue, right?
Right. And so all of this analysis you have done is in the kind of continuum setting, right? Like
Yeah.
the even though you did some numerical, so have you seen or have you looked at whether this techniques of these discrete microlocal analysis, this the microlocal analysis of
Yeah, that's a good
on the
question.
torus apply to kind of discrete, really doing a numerical
Yeah,
approximation?
that's a good question. Yeah, so I haven't seen people doing that in the discrete sense. This is a good question. And in my idea, if you want to analyze the accuracy in the discrete sense, you need a discrete version of this lemma to make it work.
Ah, okay.
Yeah,
Mhm.
you need a numerical discrete cancellation mechanism similar to this lemma so
Mhm.
that you can do the analysis. If this lemma failed in the discrete sense,
Yeah.
then you go back to this accuracy.
Mhm. Mhm. One last thing. Typically, if you once you do the delta regularization,
Yeah.
doesn't applying this frozen Gaussian approximation naturally impose the omega regularization in some sense? Like, doesn't the typically if you apply a coherent state or Gaussian wave packet due to exponential decay in phase space, it'll already cut you off away from zero, unless p is equal to zero itself. So away from zero, do you really need this kind of omega part, or isn't it somehow?
Numerically, it's easier. You are
Okay,
asking numerically, right? Numerically is easier. Numerically,
okay,
when you get close to there, you can just ignore it.
okay, yeah,
Yeah, you just do you do a if check, right? So if that's Gaussian, you just ignore it, and because it's very rare that you get into it, but analysis you have to consider that part.
sure.
Yeah.
Okay, thank you.
Yep, you're welcome.
So, are there any more last round of questions? Or otherwise, let's thank the speaker again for a very very interesting topic and some very very interesting techniques here. Thanks so much.
All right, thank you.